Okay, thank you everybody. Time for the final presentation of today. Dr. Frieda Hayek from the University of Applied Sciences Kempten and Geronimo Mann from EOS will explore the potential for additively manufactured compliant mechanisms in automation. So they're going to be talking about how flexibility-based designs can simplify components, they can reduce costs and improve reliability, and they'll be showing us that how supported by modern simulation tools. So, gentlemen, thank you. Over to you.
Thank you for the kind introduction. Hi, everyone. My name's Frieda. I'm professor at the University of Applied Sciences in Kempten at the Institute of Production and Informatics. And today, Geronimo and I will give a talk about flexible components, and we want to demonstrate why we think that flexibility is key in products made with additive manufacturing today. So within the talk, within the next 20 minutes, we want to guide you a little bit through our joint development. So we did the development together between the university and EOS. It's all about automation tasks. We just saw a gripper system already. We also want to present a new kind of gripper system that you can see here in a rendered image, but it's also actually working, and we will demonstrate you how that works and how we came up with the idea, and also what we need to design compliant mechanisms in a way as we did. Also, we want to talk a little bit about a potential outlook and welcome you to join the discussion about potential applications and requirements, because what we'll look at today is actually a prototype that's not been existing for a very long time, to be honest. So regarding the Institute of Production and Informatics, just to introduce ourselves a little bit more in detail, we are a rather new research institute south of Munich in the beautiful Allgäu area in Sonthofen. We are around 30 researchers working in a very interdisciplinary field, in the field of digitalization and production. Some of our research areas are, of course, additive manufacturing, but we're also working in the field of machine learning and data-driven optimization in production systems, also in digital twins. We're also managing our own network in the field of Industry 4.0. So if you're interested in what we're doing there, we're having frequent events also in the field of additive manufacturing. You can have a visit on our website and register for some emails or follow us on LinkedIn. We would be happy to welcome you there. And Geronimo, you want to introduce yourself and EOS a little bit more?
Hello, also from my side, some words to me. I'm an application engineer at the EOS Additive Minds team for over 5 years now, and I'm responsible for all the design for AM topics on the polymer side. So EOS was founded in 1989 near to Munich in Germany and is still a family-owned company. And we provide solutions for industrial 3D printing based on the powder bag technology, and for both, for polymer and as well as metal 3D printing. Solution means for not just the system, we deliver end-to-end solutions and support our customers from the part design and data generation to the part building and the post-processing steps. So in our ecosystem, for example, we have a lot of partners and for post-processing technologies, and we work very closely with them to develop the best process chain for the individual application. When we talk about applications, we all know it's not just the printing. There are some more things to do to get the final product. So in the past 35 years, we had a lot of customer projects, and because of that, a huge know-how in the fields and industries such as medical, aerospace, tooling, lifestyle products, and automotive. So especially the Additive Minds group is the technical consulting department of EOS with the three pillars, training and education, application engineering, and the consulting. Our team, for example, can work with your engineers to optimize, validate, and scale up your industrial 3D printing process. So always support your team to identify suitable applications for 3D printing and enable them to modify part designs to maximum the AM benefits. Because we are here to provide solutions and not just products. Okay, that's it for marketing stuff. But solution, that was the right point. The powder bed fusion technology brings a lot of freedom in design and therefore a much bigger and wider design solution space. To exploit this huge potential and get know-how in another DFAM topic, we have launched this cooperation with the IPI. And the main objective is investigate and research in the field of compliant mechanism, the so-called rising star under the DFAM disciplines. In a few minutes, you will learn more about this term and what that exactly means. So, yeah, we decided to start in the field of robotics. In detail, we talk about end effectors or end-of-arm tools for different pick-and-place tasks in the automation industry. So worldwide, there are more than 4 million robots installed. And we know that 3D printing is already a game changer when it's necessary to have lighter, simpler, and smarter end-of-arm tools. And the potential to reduce the energy consumption, for example, due to lighter grippers is huge. And in times of sustainability and responsibility, it's very important. Yeah, conventional grippers undoubtedly have their place and have proven themselves in many applications. They provide robust and reliable mechanism and are well suited for standardized tasks with low customization requirements. However, 3D printed grippers open up entirely new possibilities. And here are just 2 examples. The Siemens battery gripper is much lighter than the original one due to topology optimization. And they reduced the number of parts from 30 to 5. And due to the new and lighter design, they are also able to use a smaller robot. So the gripper for LMD provides air channels and is made from just one single part. So complex pneumatic valves with many tubes and interfaces are obsolete. So as you can see, there are a lot of very good solutions on the market, and that's really fine. But we asked ourselves, what's next? Does it work without any media? No electricity, no air, just a robot combined with our technology. And that brings us directly to the topic of today, compliant mechanism.
Okay, so before we jump into the actual development of the gripper, I want to introduce you the field of compliant mechanisms a little bit more in detail. So who has dealt with compliant mechanisms before here in the group? Just hands up if you have developed or designed the compliant mechanisms. Okay, not that many. So what is a compliant mechanism? It's actually a mechanism that provides a specific function only through elastic deformation of the structure and the material, as you can see here. Is it something really new? No, not at all. It actually exists for as long as humanity exists, if you want to say so, in nature. So you can see this here in the fly trap, which is actually a compliant mechanism because it uses a flexible, solid hinge that can, well, provide the function of the fly trap. When a tree is hit by a storm, it will bend to avoid being damaged. That's also a compliant mechanism that's already available in nature. In technical areas, we don't see that many compliant mechanisms today on the market. Here are some few examples that you can all find online that have been developed. And the basic advantages of a compliant mechanism compared to a conventional mechanism is that we do not have the need for bearings and hinges anymore that might risk damage or wear. We can reduce the part count. Actually, the part count of our joint development is also 1. Yeah? And we can reduce complexity. So it can become potentially really cheap to use a compliant mechanism to provide a specific function. We have less wear and low maintenance, and maybe also, as you said it, in combination with automation systems, less energy required because we can go really low weight with such a mechanism compared to a system that requires valves, pneumatic cylinders, electric drives, and so on. Of course, everything has a cost, and the cost here is that to design a compliant mechanism, you need to think carefully about the structure, because when you use solid hinges that need to flex to provide a certain elastic behavior, you have to know what you do, because otherwise it will simply break. And you can believe me when I say we broke a lot of those prototypes before it started working. So you also want to be as precise as possible. So you have to know about the material properties and the material behavior under large deformation. Okay, so these are the basic challenges of those compliant mechanisms. And in order to do this, you can, of course, use some advanced calculation methods, or also maybe start with very basic calculation methods. And what we wanted to show you here is a basic design path that you could follow if you want to start to develop your own compliant mechanism. I hope everyone will do after the talk. Yeah? So the first thing that you need to realize is a specific motion. You want to create a motion path that enables your function without starting to directly calculate the structural behavior. So the first step will be without any mechanics involved, without any elastic deformation and so on. So once you have the motion path developed, you can integrate some more structural mechanics in that design path, for example, by using analytical equations that have been there for a while in mechanics. For example, so-called pseudo-rigid body models. And if you're pretty sure that your compliant mechanism is already providing the function, then you can start optimizing it by, for example, finite element methods or topology optimization. With each step in the design phase, we will increase the model complexity, but also increase the design maturity to come up with a final design that's actually working properly without the risk of breaking and failure. So what we wanted to design with those compliant mechanisms is actually a media-free gripper solution for robots. You can see that we have tried many different types of geometries and mechanisms within. Not all of them, as I said, work properly, so failures were definitely part of the plan. It was not a straight design path that we followed, as I just showed here. There were some steps in between, and of course, a lot of trial and error. Yeah? But the basic requirements is that we provide a very simple function, which all of the existing robot solutions, gripper solutions provide, which is grabbing an object, holding it, bringing it to another place, and releasing it. So the function is actually very simple. But we wanted to do it just with one monolithic part. We didn't want to have any assembly. And the most important thing that we mentioned already is we didn't want to have any additional actuator, no electric drive, no motor, and no media like pressurized air that is required. And here you can actually see the final solution, or a small part of it. We will have a look at it more in detail in a second. And some of the intermediate calculation methods that have been applied by the team to calculate the stiffnesses and the deformation behavior roughly, so that we reach a specific width change of, in this case, around 4 millimeters that enables us to grab this ball, fixate it. And what you do not see here, what is actually the magic of the mechanism, is inside this central object. So if you want to know more about what's happening inside and how it works, you can see that at the booth. I don't know why it vanished just for a second, but we will go further. Geronimo. So the videos cannot be shown. Can we give it a try? Okay. Thanks.
push one more.
Yeah.
Yeah, perfect. As we can see, it works, and just a robot in our 3D printing technology makes that possible, and thanks to compliant mechanism. So the pick and place process can be activated by the robot's movement, our gripper, and the product itself to be gripped. Basically, the two grippers work differently in their heart. So on the left-hand side, we work with compliant mechanism based on torsion, and on the right-hand side with bending. And we would love to see you at our booth at Hall 11.1. This is this hall on booth D41. To show you how it works in detail. By the way, if you visit us, and you can one of these nice bouncing ball if you want to. It's made of TPU. But as wonderful as it is that it works, there are still questions to be answered. How long does it work? For example, how many cycles does these flexible hinges withstand? The short answer is we have to test it. But good news from one of our customers, their specific test part with flexible hinges achieves more than 35 million of cycles with this material, and it's made of PA1101. So another question could be, can I use this material for food contact applications? So we are very happy to announce that our PA2200, the PA12-based material, is now ready to come in contact with food. And we now have the DOC. That means the Declaration of Compliance. So the ingredients are ready for generating the next level of gripping devices with PA12. So for PA1101, the PA11 based material, we will have the DOC end of this year, I hope. Okay. Thank you from my side.
And also from my side, and of course, this has only been possible not just with the two of us standing here, but with the whole team behind. So the team is also here. Maybe you want to say hello. So thank you for the team. Thank you for listening. We would be very happy to welcome you at the booth, answer your questions, and of course invite you to a discussion for potential applications. We would be happy to find some potential users of those types of gripper systems. Maybe it will then look differently depending on the part, but we are very open to design new types of those gripper systems together with our collaboration partners. So thank you very much.
And don't forget, we have these cool bouncing balls. Not don't forget.
Thank you very much.